Good afternoon. Hello, my name is Lucinda Offer. I'm the Education Outreach Officer for the Royal Astronomical Society. It is my pleasure to welcome the last talk of the season, our last RAS public talk. We have James Hammond, Professor of Geophysics at Birkbeck University of London. And his research uses seismology to image inside the Earth. A recent focus is on imaging and understanding how rocks melt and how this melt migrates and is stored in the Earth's crust and mantle. He conducts large field projects working in the UK, East Africa, Chile, China, and the Korean Peninsula. James has recently led projects to study Mount Paektu, a volcano that straddles the China Democratic People's Republic of Korea border. This project is an example of how science and diplomacy can work together, led to the development of the Mount Paektu Research Center, of which James is director. The center focuses on development of new scientific collaboration with DPRK scientists on Paektu and other areas of environmental science. James teaches geophysics and scientific computing and data modeling at undergraduate level. He is a Secretary of Geophysics for the Royal Astronomical Society, the UK Chair for an International Union of Geodesy and Geophysics, the IUGG, and Treasurer for the British Geophysical Association. Please welcome Professor James Hammond.
Thanks, Lucinda. Yeah, just turn these lights down.
Thank you.
You see is that better? See that okay? Great. Yeah, thanks, Lucinda. It's real great to be here. This is the second time I've given this talk today, so hopefully I'll try and keep the enthusiasm levels up. And what I want to talk to you today is about this volcano, right? This beautiful, spectacular volcano that sits on the border of China and North Korea, or I'll probably refer to it as DPRK just out of habit. That's kind of the more formal name for the country. And I took this photo in 2013, October, and I'm standing on the Korean side of the volcano, looking across Cheonji. This is Cheonji Heaven Lake, and on the other side of the lake is China, right? And so the border literally runs right the way through the middle of this caldera. And so from a scientific point of view, it's fascinating, but from a political point of view, it's equally complex and interesting. And in the talk tonight, I'm going to talk a bit about the science, talk about how we got involved working on this volcano, what we've been doing to try and understand it in more detail. And then I'm going to finish the talk talking a little bit about the diplomacy aspects, like how the project got up and running, how we've managed to sustain a 14-year collaboration. And as we kind of seem to be entering something of a geopolitically more turbulent time, let's say, whether there's any lessons we can learn about science collaboration that may help going forward. And first, just want to thank a lot of people that are involved in doing this work. On the left-hand side here, all these names are what I would call the scientific kind of team that's been involved in this. From the Earthquake Administration, State Academy of Science, Kim Chek University and Kim Il-sung University in the DPRK, the China Earthquake Administration in Beijing, and then colleagues at Birkbeck and Cambridge. And then on the right-hand side here are what I would say is more on the diplomacy side, on the logistical side. People at AAAS, Norm and Rich Stone, and the Royal Society here in London, who've been instrumental in acting as advocates for the project, in helping us navigate what has been the complex kind of sanctions side of things. And then the Environmental Education Media Project in Beijing and PinTech in the DPRK. And I haven't named up here, but equally important is the British Embassy in Pyongyang and the DPRK Embassy here in London. Three people I want to highlight in particular are Ri Kyung-song from the Earthquake Administration of DPRK, Yu Wei-shan from the China Earthquake Administration in Beijing, and Sunri Han, who was working with me here in London, but is now at Jilin University. All the science I'm going to present today These are the guys that have actually done it, right? The PhD students and postdocs and scientists that have worked on that. Okay, so going back to Mount Paektusan. Right, here's another picture of Mount Paektusan. It's impossible to take a bad photo of Mount Paektusan. It is an absolutely spectacular place. And here we are again. Look, this is from the Chinese side of the volcano, looking into Heaven Lake again. And the name Mount Paektusan, or Changbaishan as it's known in Chinese, means forever white mountain. And the reason for that is it's either covered in snow, so for 9 months of the year it's covered in snow, or it's covered in all of this white rocks that you can see in the foreground here. Right, this is pumice that's been erupted from a huge eruption in the year 946, thought to have formed this 5-kilometer wide caldera that we see in which the lake sits. And it's got this very characteristic white color, right? So the volcano always seems to have this white head to it. The ash from this eruption and the pumice is found as far away as Japan and the Kuril Islands, and it's even found in the ice cores of Greenland, right? Showing that the ash got up into the stratosphere and managed to travel around the whole planet. And this just shows that it was a big eruption, right? This eruption in the year 946. And if we put that into comparison with some other more well-known eruptions, so the purple circle here is representing the size or the amount of material that was erupted in this eruption in the year 946. You can see it's comparable in size to Tambora, which is the biggest eruption in human history. It's about an order of magnitude bigger than Krakatoa. Anyone who went upstairs and saw the picture in the book from Krakatoa, right? It's an order of magnitude bigger than that. 2 orders of magnitude bigger than Vesuvius, 3 orders of magnitude bigger than Eyjafjallajökull, the eruption that stopped all the air travel around Europe. And so to put it into terms of something a bit more visual, it's enough material was erupted from this 946 eruption to bury the whole of Greater London in about 60 meters of ash. Right? This is a big eruption. It's probably easily up there in the top 10 eruptions in human history. Right, so for volcanologists, we've always been fascinated by this volcano, right? But its location, you know, remember the border running right the way through the middle, meant we never really thought we'd have the chance to work there, to study it and understand it. That changed, though, in the beginning of the 2000s when Chinese scientists monitoring it on their side, DPRK scientists monitoring it from Korea, noticed a period of volcanic unrest on the volcano. And this manifested itself as lots of small earthquakes happening and located directly beneath the volcano itself. They saw changes in the amount of gases that were emitted from the volcano. They saw ground deformation, uplift, all associated with magma moving beneath the volcano. And this caused a lot of concern in China, across the Korean Peninsula, in Japan, and much wider, that this volcano was waking up. And so this led to, actually, at this point, I like to point out that the volcano is now very quiet. Right? So don't all run out in a panic and think it's going to erupt at any moment. But it definitely showed that it's one that has the potential to erupt again in future. So this led to scientists in DPRK issuing an invitation for international scientists to travel to Pyongyang and meet with their scientists to discuss potential collaboration. And I remember it well. My colleague Clive Oppenheimer phoned me up in my office and he said, "What are you doing in 3 weeks' time?" I said, "Not much." He said, "Do you want to go to Pyongyang?" And I think I said to him, I said, "Clive, you know me too well, don't you?" Like, "Of course I'd like to go to Pyongyang. That sounds like a great trip." And so we, jumped on a plane, and here we are. Here's, sorry, going the wrong way. Here's Clive and I, both looking a lot younger in 2011, arriving in Pyongyang for the first time on our Air Koryo flight. And what we did on this trip is we chartered this whole plane, and we filled it full of scientists from DPRK. and we flew up to Samjeon. And here we are in Samjeon. This is with the Earthquake Administration of DPRK. We had a journalist from science that traveled with us, and some filmmakers from the Environmental Education Media Project. And we spent about 2 weeks up on the volcano, and we visited some of the key eruption deposits, right? So this is a sequence of pumice that was erupted during the 946 eruption. So you can kind of look in here, the different layers telling you different stages of the eruption. We visited some of the hot springs out on Chonji Lake. And we visited a number of their monitoring stations, you know, where and learned about the efforts they were doing there. We were told we're the first Western scientist ever to be granted access to this location. And this was great and really fascinating and a lot of fun. But what was the highlight of the trip was that we just sat around with these scientists in DPRK. We took a projector with us. We sat in the Begabong Hotel, and we had loads of discussions about volcanoes. And we talked about the volcanoes we'd been working on around the world. We learned about the decades of research they'd been doing on Paektusan volcano. And we quickly came to a realization there's a whole bunch of really fundamental scientific questions that we could work together to try and address. You know, and they range from, you know, why does the volcano even exist? You know, why is it there? It doesn't sit on a plate boundary, right? So it's not like the Ring of Fire kind of volcanoes that we all know about. It's what we call an intraplate volcano. And there's some hypotheses, but very much debated as to why we even have a volcano there at all. We don't know its history very well. We know about the 946 eruption, but we don't know about older eruptions or more recent ones. So we don't know if this big eruption is typical or atypical. And if we want to know what's going to happen in the future, well, the only clue we have for that is how often and what style of eruptions it has in the past. We don't know what triggers the unrest and the eruption, right? What clues can we look for when we're monitoring to understand what might trigger a future eruption? We don't know what the state of the volcano is. Where's magma stored today? How much is there, and how does that compare to what it was like before the 946 eruption? And all of this feeds in to understanding what the risks of a future eruption are for the local, regional, and wider populations. Right? So really key fundamental questions that we felt we could work together on. Now I'm going to talk a bit, we kind of went away from this meeting full of enthusiasm, we got some funding, and then we hit a lot of hurdles, right? And I'll talk about those at the end of the talk. I'm going to focus first on the science. And what I'm going to focus most of all is this question of what is the current state of the volcano? Where is magma stored today? Because I'm a seismologist, that's the kind of research that I like to do. And I'm happy to talk or answer questions about any of these other points up here. Now, the motivation for us as geophysicists was pictures like this or cartoons like this, which have been drawn, in this case, by a petrologist, right? And a petrologist, what they aim to do is take the rocks that have been erupted during the 946 eruption or other eruptions, and they look at the composition of those rocks. Rock minerals and elements are present within that rock. And a unique combination, that unique composition of the erupted deposits, they try to recreate that in the lab, right? And it tells them about the pressures and temperatures that the magma was sitting in and being stored at just before it has erupted, right? So they try and build a model of the volcano, what it looks like just before it erupts. So I'm just looking for my pointer. And so this is what they have on the left-hand side here, right? So this, what they're arguing is that there's some deeper, kind of more primitive magma that represents the longer-term storage of the volcano. And then there was these two quite shallow, one more evolved, one a bit more primitive magma reservoirs that were sitting there for a long time, were quite cool, quite silicic, full of crystals. And basically what happened was magma was injected from this deeper one into these shallower regions. It triggered that to kind of become unstable and mix and led to this very catastrophic large eruption. And they argue that today, they speculate that this deeper magma reservoir might still be present, but these shallower ones are probably quite cooled, full of crystals. There might be a small amount of magma, but not too much left. But it's this interchange between the two, which is interesting and might tell us about what is driving the eruptions in this region. But you can see there's no numbers on this. Right? There's very few depths because it's quite hard to constrain. There's no idea of how big or small these features are or whether they exist today. And that's where geophysics can come in, right? Because geophysics is a tool by which we try and provide a snapshot of what the inside of our planet looks like, right? And the common and probably rather labored analogy that we often use as geophysicists is we can treat the Earth a bit like a doctor treats your body, right? And if anyone's been unfortunate enough to have to go to hospital and have a CT scan, rather unpleasant process where you get put in this big tube and it's very noisy and you can't move. And basically what's happening is an X-ray source is rotating around and around your body, firing X-rays through your body. And on the other side, there's a bunch of sensors that measure how much of that energy makes it through. And depending on what it's traveling through, bones or tissue, it absorbs X-ray energy by different amounts. And so if you fire that energy in enough different directions, you can work out where the really absorbent bits are and where the less absorbent bits are. And then you can build a 3D image of the inside of your body, right? And we get these incredible non-invasive way you can see the insides and if there's any issues. So as a geophysicist, we want to do the same, right? But we want to do it on a volcano rather than on a person. Now, of course, we can't use X-rays to do this. So we need some other form of energy that probes the interior of our volcano. And so what we use for this is seismic waves, right? Because seismic waves, when you get an earthquake or an explosion, or even if I just stomp my foot, you can kind of feel those vibrations, they spread out, right? They're traveling through the floorboards, they're deforming the material as it travels through. And in the earth, as that seismic wave travels through, it's deforming the rocks, right? As it passes through. It's basically a sound wave that's traveling through the earth. And the speed that that wave travels at depends on the stiffness of that material, depends how strong it is, basically. Right? And so if you've got a very dense cold rock, then seismic waves will travel quite fast. But if you have a lot of magma or melt, or if it's hot, it will be weaker. And so the seismic wave will travel slower. So if we can measure how long it takes, say, to get from our earthquake to our seismic station, and we get enough different paths, just like the doctor using X-rays, we could try and build up a model of where the slow bits and the fast bits are, and we can interpret that to say whether there's a magma chamber or not. So what we need is to go to this volcano or any volcano with a bunch of seismometers, deploy them, and then wait long enough for enough earthquakes to happen, either locally or we can even use earthquakes all over the world. And then we can build up an image of the inside of this volcano. So that's what we did. So in 2013, we went back to DPRK and we hired our kind of Russian Tupolev plane from Air Koryo. And this time, instead of just filling it with scientists, we did have a lot of scientists on there, we filled it full of our seismic equipment. This is the business class section of the plane, full of all of our seismic equipment. And here I am testing it at the Baekdusan Hotel, right? So these are broadband seismometers, don't look like much, right? But they're very, very sensitive pieces of equipment. They could basically record, you put one of these, deploy it well, you can record any earthquake that happens anywhere on the world above about a magnitude 6. Right? So pretty, and it basically measures the very small nanometer kind of ground motion. Very, very sensitive bits of kit. And so what we did is we deployed this as a 60-kilometer long array within the northern part of DPRK. And the reason for this array is we wanted to look at the crust, but directly beneath the volcano, where we think the magma is being stored, compared to crust over here, which is just on your bog standard normal continental crust. We don't think there's much volcanism. And we left these stations recording for 2 years in the ground. We brought them back in 2015. Here's just a couple of pictures from the field. So this is the site on Jangun Peak. This is right on the edge of the caldera. It's in, you can see, this is Ri Kyung Song here, installing the seismometer at the back with a colleague of his. And all of these buildings are owned by the Earthquake Administration of DPRK. Right, so this is really handy. We could use their facilities, their monitoring stations to put our stations in. But as we got further from the volcano, we couldn't rely on their support anymore because understandably, all of their stations are quite close to the volcano, right? They're there to monitor the volcano. So we had to work with local communities in DPRK. So this is the village of Sinmusong. You can just about make out down here, they gave us a small plot of land in their potato field. And we built a little concrete bunker and we put our station in here. We've got a GPS antenna here, which is for accurate timing. And you can just about make out our solar panels on the roof of this building and then the cable going in the window here. And inside was our batteries, and the family that lived here would look after this station as well. They actually looked after us pretty well as well. They picked some blueberries and they brought them over for us to eat while we're working on the station. And having this support was so important, right? Because this is August, and August on Mount Paektu is glorious, like mid-20 degrees, lovely, maybe the odd shower. But just 2 months later, this is what it looks like on Mount Paektu, right? So I was lucky enough to go there in October. It's the picture from the opening slide. At this point, the roads are impassable. You know, we had to hike up to the top of the volcano through kind of knee-high snow, carrying all of our equipment. And I think there's a little movie here that just shows you kind of what it's like up on the volcano during this time. You know, I'm inside here just wrapping up all of our seismic. So already by this point, it's about -10 degrees centigrade. In January, February, it gets down to about -40 on top of the volcano, right? It's pretty extreme. And so having the support of these local communities and the scientists meant that they looked after our stations for us. When the solar panels were covered in snow, they went out and cleared them, right? And if it's too windy, they brought the solar panels inside so they didn't blow away. It did happen to one of our panels, right? So, you know, they really helped us get really nice data recovery. The other part of the collaboration was we're really pleased that over a number of years, scientists from DPRK could come and join us here in the UK, spending time with us in London, in Cambridge, working on the seismic data, analyzing the rocks in our lab. And here's Ri Kyung Song, the lead author of our first paper, presenting his work at the Royal Society. And this is the first ever engagement the Royal Society had had with people from DPRK. So that was quite an exciting event for all. Okay, so let's talk a little bit about what we found out from the seismology. So the first method I'm going to talk about is a method called receiver functions. Okay, now receiver functions use earthquakes that happen all over the world, right? We're not looking at earthquakes on the volcano. And an example here is, let's say, an earthquake that's happened in the Himalayas here, and it sends that seismic waves traveling throughout the planet, right? And some of that will bounce off different layers within the planet. This little movie showing reflections and refractions off the core, for example. And that energy travels around the world, and then we can record it on our seismic stations, such as this one here. This is actually Incheon in South Korea, right? And we get these bumps and wiggles in our seismic data here. And the job as a seismologist is to interpret all of those bumps and wiggles, right? Work out where it came from, what it bounced off, how deep that layer is, how fast the mantle is, those kind of things. Now, if we have a lot of structure directly beneath our seismic station, let's say a magma reservoir, then some of that energy will bounce and reflect and refract off that magma chamber. So what we try and do in receiver functions is we try to isolate that energy, right? We try to isolate that energy within our seismic data so it can tell us something about where we have sharp changes in velocity directly beneath our stations. Now, to do this method, we used our 6 stations that we deployed in DPRK, and that's what Ri Kyung-song first published on. But then we worked with the China Earthquake Administration as well to bring in some of their data that they'd been recording over many years in China. And this is really exciting. It's the first ever time anyone had done a cross-border analysis of this volcano. First time we brought Chinese and DPRK data together. So let's have a little look at what we see, right? So this strange looking plot on the left here is how we plot receiver functions. I'll talk you through it. So here at the top, this is the topography, right? So you can see there's a classic volcano kind of shape, right? This is the caldera here, and Chongji Lake sits in the middle, right? And then these wiggles down here, these are what we call receiver functions. And where you see a black kind of peaks in the data, this is saying at those depths, so this is between about 30 and 40 kilometers depth, there's an increase in velocity, in seismic velocity at that depth, right? And what you're looking at there is you're going from the crust into the Earth's mantle, right? And there's a sharp change in velocity at that depth. And you can see that directly beneath the volcano here, there's a thicker crust, right? It's about 40 kilometers thick here compared to about 32, 33 kilometers outside. And this is quite typical for a volcano, right? Because over 1 million years, you've been injecting magma or melt into that crust. A tiny fraction of that comes out of the top in eruptions. The rest gets stuck, right, in the crust, and it builds it up over time. So this is quite common to see on a volcano, this thicker crust sitting beneath the volcano. What was really exciting to us were these gray peaks here, right? And these gray peaks are showing the opposite. It's showing as you're going deeper into the Earth, the seismic velocity gets less. And that's very unusual, right? Because normally the density increases, rocks get stronger, seismic waves travel faster. And so this was telling us that at that depth, at about 8 kilometers, we seem to be seeing the top of what could be a magma reservoir, right? So you've got magma sitting there, it's got lower velocities, so as you go deeper down, you're getting this signal related to this low velocity layer. So this is our kind of first little clue that, okay, yeah, we think we've got a fairly sizable magma reservoir sitting beneath this volcano today. So the next step was to think, okay, just like that doctor using his X-rays, can we use more stations to see if we can get a 3D representation of the structure beneath this volcano? So this is not work that I did. This is work by someone called Xingli Fan at Chengdu University. And he took our seismometers here, these purple triangles, and combined it with data across Northeast China. And so you can think about this like, you know, looking at seismic waves traveling to all of these stations. You can try and work out the fast and the slow parts. And you can build up a 3D model of where the fast and slow velocities are, right? And so in this map on the side here, the blue regions are fast velocities, the red regions are slow. And indeed, you can see beneath the volcano here, we do see this region of slow velocities in about 8 kilometers. And they extend, in this model, they extend pretty much throughout the crust, right? But you can see these are relatively low resolution. And the reason for that is the stations are spread out quite far apart, right? Apart from our stations are quite dense, right? And it's great to see the data being used in this way. We made our data publicly available exactly so anyone can download it and use it. But we thought we could improve on this. Just like that doctor using X-rays, if we put more sensors out, right? If we put more seismometers out around the volcano, we improve that density, then it should help us improve the resolution of our images, right? And so you can see the red diamonds here are all the extra sensors that we put out in collaboration with the China Earthquake Administration. The other symbols are stations that Xingli Fan would have used in his model. Right, so by having this denser network, we should be able to improve the resolution of our models. And indeed, that's what we do, right? So at the top here, these are the kind of models that we would get from a station distribution that Xingli Fan had. And you can see that we have about, we could resolve, or Xingli Fan could resolve anything above about a length scale of 100 kilometers. Right? That was the minimum size of any feature that you might be able to see. With our new data, we improved this about 5-fold, and we have a resolution, we can resolve features above about 20 kilometers. Right? And you can see that these models are pretty consistent with each other. They're showing the same thing. It's just we have much more resolution in these lower models, simply by deploying lots more seismic stations in a denser array. And so Yue Shan, the PhD student who worked on this, produced these really rather nice models, right? So we can go from this kind of blurry kind of image that you see at the top to getting a much more detailed image of what the crust looks like beneath this volcano. And what we see indeed at a depth of about 8 kilometers is quite a focused low velocity zone, right? That we interpret as this magma reservoir, right? Here it is in map form at 10 kilometers depth. You can see it located right beneath the volcano. We see this actual region of faster velocities sitting in the lower crust with lower velocities in the mantle, right? And so we can then interpret this in terms of what's the magmatism, what's driving volcanism in this region. And so we can go back to the models, Pambo's models, based on the petrology, and we could start putting some numbers on this, right? So we can say, well, this deeper, more primitive magma chamber, that's what we interpret as this thing at about 8 kilometers. These shallower chambers, maybe we see them, but it's even with our dense stations, we lack the resolution to really image these small features. And then actually what we're seeing is this whole thing is fed from the mantle and actually doesn't spend much time in the lower crust at all. That melt goes in, it works its way up, and it's getting stored at a depth of 8 kilometers. And it really suggests that that long-term magma reservoir is still chock full of magma, right? We reckon about 2 to 10% melt fraction in that region. Is big error bars on that, to be honest, right? But so it's not a huge amount of melt, but it's definitely this whole mechanism. We can use this now to see how that changes over time, how that relates to volcanic unrest and the like. The last thing I'll say on the kind of scientific side of things is when we designed this deployment in China, our original plan was to also have stations deployed more stations deployed in DPRK. And we still hope to do this. We have funding to do this. We have all our permissions in place. Our plan was to do the deployment in summer 2020, right? So we all know what happened instead, right? COVID got in the way. And DPRK has very slowly been opening up after that. So we're waiting for travel to be possible, and then hopefully we can improve on these images even more by deploying our seismometers within the DPRK. Okay, so what I'd like to do now is to take a step back a little bit and spend the last 10 minutes or so talking about the more diplomacy side of this project. And when we started this project 14 years ago, the world was quite a different place, right? And I think you'll all agree that there's been a lot of turbulence on the Korean Peninsula over that time. You know, changes of leadership in all of the countries involved in the region and involved with our project. There's been provocations on the peninsula, nuclear tests, missile launches, joint military exercises that the DPRK see as very provocative, UN sanctions imposed off the back of these. And we've obviously had COVID as well. And this has created quite a difficult environment for us to build and sustain a scientific collaboration with our partners in the DPRK. Now, there's two big factors why I think we've managed to do this, and two groups that we're really grateful for having their support. The first is the Royal Society and AAAS, what I would call like National Academies, Learning Societies. And a year before we started our work, the Royal Society published this seminal report on science diplomacy, right? Now, science diplomacy is not a new thing. We've been doing it for as long as we've been doing science and having international kind of relations. But this really formalized the idea that science could be used for diplomacy as a tool to build relationships, to build trust and understanding when more traditional forms of diplomacy are rather strained. And indeed, we see this, whether it's Nixon going to China or the USSR, Kim Jong-un meeting Moon Jae-in on the slopes of Mount Paektu during the summits of 2018. Science was always one of the first things that people talked about as an engagement, right? It's easy to build something around mutual interest, common language. Science is a brilliant thing to do that. And the Royal Society and AAAS recognized in our project that there was an opportunity to do that, built around understanding this big volcano that seems to be showing signs of life, in which the DPRK are looking for international collaboration. So they acted as advocates really for us, right? And they helped us navigate the complex world of sanctions, of which we had no experience whatsoever. The other side of the coin was the UK government, right? In the UK, we have an embassy in Pyongyang. We have done since about the year 2000. And we have a permanent seat on the UN Security Council, which gives us a unique position on what's going on within the DPRK. And the UK's foreign policy is one of, towards DPRK is one of critical engagement, which means they're critical about the DPRK's nuclear weapons of mass destruction development, human rights record, for example. But, and I think this is summed up really nicely by Mike Cowan here, is that the UK pursues other forms of engagement with the DPRK to try to increase the level of mutual understanding and hopefully reduce the level of disagreement between the two sides. And having a significant impact will only be possible in the longer term and requires continued and consistent commitment. And it's easier to build up this kind of exchange if efforts are focused on areas where the two sides see mutual benefit. And they recognized in our project, again, that there was a chance to do this, built around an area of mutual interest. And so they worked quite hard to help us get this project running. So without that diplomatic support, creating space for the science, so-called diplomacy for science, I don't think we'd have been able to achieve what we did. This is not to say it didn't come without challenges, right? It took about 18 months to have those initial discussions with the UK and the US government. And even at the end of that, we were refused permission to take some of the equipment we wanted to take. So we wanted to do a method called magnetotellurics, really good at measuring the Earth's conductivity, right? And if you've got fluids, conducts electricity well, so it's really good for finding magma. And actually, Kathy Whaler, I can see her picture looking at me on the wall over there. It's one of she was going to lead this element of the project. We went through the whole process, and we found out during this process that apparently the induction coils we use to measure the magnetic field really accurately can be used to detect submarines, right? So it sits on a list of equipment that's called dual use that has civilian and military applications. And so we were told we can't take it to DPRK. So we had to revise our project. We went from a 1-year seismic deployment to a 2. We had to go to our funders and explain to them we might need a little bit more money because we now have to do 2 years of deployment. We had to explain to our Korean colleagues sanctions are stopping us doing this, right? But we could be flexible, and we could still achieve our scientific goals. And we still have to do this process. We've made 18 export license requests. We continue to face challenges currently around laptops, for example. We struggle to take them to DPRK. The other issues around sanctions is they constantly change. And in 2016, following a nuclear test, the UN Security Council put new sanctions on DPRK that said all science shall be suspended. I was like, oh, this is a problem. And we just published our first paper. We just held a big conference to explore new projects, and it looked like nothing was going to happen. But we went to see the British Embassy. We went to the SCDO down the road, and we went to see the embassy. And they explained to us that this whole policy of critical engagement is built around continued and consistent engagement. There's no point trying to build these relationships if you keep stopping and starting it, right? Because you don't build that trust and understanding. And so they said, look, we'd like to see if we can keep this project going in the face of these sanctions. We think there might be a way, but no one quite knows what it is. Can we use you as a guinea pig? We'll work with the UN Security Council, and we'll see if we can find a mechanism by which your project can continue. And they did, in this rather beautiful and elegant diplomatic way of writing letters to each other, right? And so the UK mission to the United Nations wrote to the chair of the 1718 Committee of the Security Council, saying they had the honor to notify them about the Mount Paektu geoscientific group's work. And the Security Council wrote back and said, oh, they have the honor to refer to this letter, and very diplomatic language. But basically, through this just exchange of letters, we got permission for our project to continue. And we've done that 2 or 3 times now. And it actually sets a precedent by which science engagement can continue in the face of some of very blanket and quite severe sanctions. And so on the back of this and all of this complexity, we ended up setting up our research center at Birkbeck here in London. And it does feel very strange to have a research center dedicated to a Korean volcano sitting in the heart of Bloomsbury, especially when I give this talk in Korea. They're a bit like, a bit nonplussed by that kind of idea. But it gave us a platform that we could deal with all the legal challenges and everything. And it meant that, despite all of this turbulence, we've been able to maintain 14-year collaboration with DPRK. And it's probably the thing I'm most proud of. I love the papers coming out, the science, but the fact we've maintained this is a really unique example of a sustained collaboration over this time. We've managed to get funding, we've managed to get our licenses in place, and we've managed to meet with our Korean colleagues, conduct field work, exchange research visits, and importantly, publish research papers. And you can see that COVID has been the biggest challenge to all of that, right? And we're just starting to pick things up again after the kind of lockdowns. So I'll finish by just saying a few words, thinking a little bit about, what are the implications of this, right? We've worked with a country under the most severe sanctions. And as we go into quite a geopolitically fragmenting world, are there lessons we can take away from that we might be able to use? And I've gone back to this report from the Royal Society in 2010. And when this was written, the world was quite a different place. And this report reflects that. It's quite got a rose-tinted view of science diplomacy, right? It talks about diplomacy as being there to support science, to build collaborations, to build relationships, and to facilitate science cooperation. Earlier this year, they've updated this report, and this is an excellent report, and I encourage people to read it, called Science Diplomacy in an Era of Disruption. And again, this reflects the world in which it's written, in that it talks about how science diplomacy, within science diplomacy, science can be used as much as a stick as it can a carrot, right? And it's used as a tool to punish as well as to build collaborations. And I think the most high-profile example of this in recent years is where, following the Russian invasion of Ukraine, their blanket sanctions on all science was imposed by in this case, the European Commission, but the UK, US, and many other countries. Right? And this targets everything, right? All science. And there's understandable reasons why that has, and then I'm not here to argue against that at all. But even in the days before this was imposed, organizations like the International Science Council were pointing out that this would have rather severe consequences to a number of areas of research. And I think it says here that our capacity to work collaboratively on global challenges and on cutting-edge research, such as Arctic and space research, is only equal to our capacity to maintain strong collaboration amidst geopolitical turmoil. And ultimately, the isolation and exclusion of important scientific communities is detrimental to all. right? Rather provocative statement, but it's turned out to be quite true. And if we focus in particular on the Arctic, for example, the halting of science collaboration has reduced our ability to understand the impacts of our warming planet on permafrost, on the Arctic, one of the biggest places that's been impacted by climate change. And there's a paper published in Nature Climate Science last year, which I think showed this quite nicely. This is the EU Interact network. It's there to monitor change in the Arctic in response to climate change. And I think it has about 92 stations that it's using. All of these red ones are in Russia, right? About 50% of the Arctic coastline's in Russia. Over 70% of the world's permafrost is in Russia. None of those stations are now reporting into international monitoring efforts. And they showed in this paper that that has increased bias in their model. It's reduced their ability to understand, to monitor, but also to predict what will happen in these areas in future climate change. Right? So the point is that having these sanctions is having severe consequences on science, right? And it's a question of whether we want to maintain some collaboration during this time. Now, we do maintain science collaboration with Russia in some areas. So, for example, the nuclear fusion reactor, ITER, it still heavily involves Russia. The International Space Station involves Russia. And CERN, while they pulled out of working with most Russian organizations, have maintained a strategic alliance with the Joint Institute for Nuclear Research. And these are largely driven by financial or legal obligations, or really embedded within national interest of countries. And what I would argue is there space to identify strategic areas of collaboration driven by global challenges, driven by those kind of topics that we really have to work together if we want to address them, or at least be able to adapt to a warming planet. And so I'll kind of leave with this image, this rather kind of provocative image, which just shows in the background here, this is the warming stripes from climate change, right? Showing the kind of 1.5 degree warming that's happened over the last sort of 50, 60 years or so. And in the foreground here, this is the number of international sanctions that have been in place at any one time. And you can see that we're at the highest point of sanctions since the Second World War. Right? And this, I think, is just showing that there's areas we need to work together, yet there's barriers to that collaboration. But I think our work in North Korea shows you can work within those restrictions, as long as diplomats, scientists, people come together with the will to actually do that. We never received exemptions. We never tried to water down anything to do with the sanctions. You can work within them, and you can still work on these strategic areas. And I guess that's what I would argue we should be thinking about going forward. And so I'll just finish by saying, I think environmental science offers not completely safe, but a safer space for science engagement, right? There's clear mutual benefits, whether it's working on climate change related Arctic science, volcanic hazards. It's relatively low risk to changing sanctions, right? We can work within that framework as long as we get the support from diplomats. And it can facilitate that long-term, consistent approach required to build trust and understanding. But it does need diplomats and scientists to engage, to understand, one, the needs of sanctions, and also the impacts of sanctions, and to work together on that. And it needs support from the national academies or learned societies like the Royal Astronomical Society, the funders and universities, to help those projects be maintained during these the most severe political strain. And I'll leave it there, and I'm very happy to take questions. Thank you.
Excellent talk, even though it's your second time already doing it today. I have a question, because I wonder, you say that the people who kind of deal with the diplomacy regarding these different countries. But have you ever had to get involved in, or have you practiced diplomacy with some of the individuals that you work with?
I guess so. I guess that I've had to develop some diplomacy skills. I mean, an example would be, you know, when we couldn't take the induction coil, so I had to go to Pyongyang and I had to stand there and explain to them that sanctions mean we can't do this, right? And that's quite a difficult conversation to have. People in DPRK are not particularly happy about the sanctions, right? So, but, you know, the discussion is, well, look, you know, we have to work within the international framework as just like you have to work within the DPRK framework, right? And we quickly came to an understanding on that. So I think, you know, those early days of building trust, as we tried to work each other out and understand each other, I think there was quite a lot of diplomacy in those days. Yeah.
You left that. I was wondering if you left that for someone else to handle on your behalf, or again, you're saying you're practicing this diplomacy or something.
Well, I think, well, actually, there's different things there, right? So we purposely would never get involved in international relations. That's for diplomats to do, right? Because that's not our space, right? And one, we're not trained in it. We don't know what to do. Don't really know what we're doing. But also from the DPRK side, they're like, you know, we're working on a science collaboration. This is not a diplomatic collaboration, right? But what we can do is we can create space for the diplomats to have those discussions. You know, so we've had events and meetings where we talk about our science, and we may have people from the DPRK embassy and the UK embassy to DPRK. They might be in the room together, and they can share that, have that discussion, right? Or they can talk about volcanoes together rather, you know, as a positive rather than having nothing positive to talk to each other about. And I think that's where the science for diplomacy comes in, is that you've got some area of mutual interest that you're working together on that's positive, even when the majority of your discussions tend to be rather negative, right? And it just shows that actually we still have things in common and areas we can work together on. And I think that's why it's quite valued by the diplomats.
Yeah.
I'm interested actually in just volcanic activities in general. If it's possible, say, looking into colonization in the future, looking in the structure of volcanics to kind of stabilize the axis of the planets. Is it possible to have that?
Sorry,
So when they're using artificial volcano stimulation to stabilize the axis, so the planet is more stable within the axis, so it's not having that kind of flips.
So so the volcano collapse, you mean, or?
No, it's like creating like a stimulating, producing this kind of like a volcanic eruptions. So, you know, like people build high buildings or well, but doing that with volcanoes, so you can stabilize the axis. So there's no that kind of polar flips happening.
Oh, I don't think so. I mean, the volcanic activity at the surface is pretty far removed from what's happening within the core of the planet, right? So, okay, you might have the odd mantle plume beneath Hawaii, but it will take hundreds of millions of years for that material to get from the core to the surface, right? So the interaction, direct interaction between the two, there's very little influence there.
Because in Venice, we know in the sky volcanic planet, so I think the planet have this ability to create environment where kind of itself and creating condition to stabilize its axis. So it's not have these flips like in the past we have this.
You mean like the magnetic flips?
Yeah. That's what I mean, because when this happened was quite major damage to the life, so it's destroyed everything. And people have to start again, kind of. So maybe this time we can maybe like do something about like using volcano for that, I guess.
I don't think so, and no, I don't think so, and also I don't think we can really stimulate a volcanic eruption either. So, fortunately, I don't think there's much we can do about that.
I noticed the South Korean flag on your funding swim lane. So where does the South Korean involvement come in, and where do they see the kind of science diplomacy wins coming from with this project?
Yeah, it's a good question. So this was during the summit era, right? So when Moon Jae-in and Kim Jong-un were meeting, and when Donald Trump and Kim Jong-un were meeting. So we did explore the possibility of some inter-Korean collaboration around that time, and we had some discussion meetings and meetings where, you know, we did have people from the DPRK and from South Korea to explore whether there's areas of collaboration there. And I think there was potential, but unfortunately then that politics kind of broke down a little bit, and it didn't really go anywhere. And I think in that area, the inter-Korean side of things is very complicated. And one of the interesting things we found is that, you know, we had a platform for international collaboration. So, you know, it's easy for us to bring in people from let's say Germany or you know, New Zealand or wherever, right? We brought people from Singapore and things like that. But on a Korean perspective, they didn't, both North and South Korea don't treat that as an international collaboration. It's a domestic thing. And that was clearly beyond, that was not in our remit, right? As working on international collaboration. So it's clear that there was tensions there that were a bit more difficult to manage. And so we took a step back and we focused on the international side of collaboration.
Thank you. Thank you very much for the presentation. I really wasn't expecting this two very different merging into one. The Campi Flegrei supervolcano near Naples has been in the news quite a bit. There's been a lot of earthquakes. In your opinion, are we anywhere near being able to predict eruptions?
Oh, that's a tricky one, isn't it? Yeah, I mean, predict is not a word I would use, you know, because that to me kind of gives the impression that, like, you know, in 6 months or even in a week, the eruption will happen. I think we're very far from being able to do that. What we can do, though, if you can carefully monitor a volcano, and if you know its plumbing system quite well and things like that, you can say, oh, you know, the chances of an eruption are increased, or the magma's reached this certain level. And they do that in Iceland now, actually quite well. That's one area where they can monitor it, and they can say, oh, the magma is this far below the surface, and so the chances of an eruption are much more increased. But even then, you know, they'll say, oh, it's a 90% chance, but then it won't happen, right? You know, and it's very difficult. In La Palma, I thought they did that quite well. They could again track the magma coming close to the surface by locating the earthquakes. But more often than not, it will come up to near the surface and then stop, right? Because the magma's frozen, it doesn't quite get there. So our ability to really conclusively say what's going to happen, we're not there yet. We're really not there.
I have a question before that, and if 2035, we are here, you've been able to get everything that you wanted in terms of the science and the diplomacy, what will you have discovered by 2035?
On the volcano?
On the volcano, yes.
So the key things we really want to work towards are a unified history of the volcano. And I didn't talk about that today. I didn't talk about the geology side of things. But one of the big questions we have there is people working in China have a different history of the volcano to the people working in DPRK. And part of that reason is they've not really worked on each other's sides of the volcano. So part of our big project was to bring those scientists together to share that information and try to come up with a unified history. And that helps us understand what it might do in the future, right? Then you can feed that into probabilistic models of what future eruption size might look like. Then you can produce hazard maps. And then really what the key thing is to work with the DPRK and China to understand the populations, the vulnerabilities, and then you can start to understand what the risks are, and then you can start to mitigate against those. Right, so that's the kind of long-term trajectory we were on when COVID hit, right? So that's kind of what we'd like to get back to, I think, working with the Koreans.
Thank you. And do you have a question?
Sure, it's a very quick question, really. Why is the volcano there? And second question, if you could have 20 high-quality stations like you had extra, or say 1,000 really cheap little stations that you drop from a drones or something like that, which would you prefer?
I should be careful because Tom's in the audience. He makes those little cheap sensors. So why is the volcano there? So that question, it is linked to the Pacific subduction zone, right? So the Pacific plate is subducting beneath Japan, right? And you get all the volcanoes of Japan in the classic way of subduction zone going down, releases water, you get melt. Beneath Korean Peninsula, Northeast China, the slab is what we call stagnant, right? It's stuck at about 600 kilometers depth, and it extends quite far under China, and it can't get down into the lower mantle. And so some people have argued that there's some more water being released at that depth, which causes it to be buoyant mantle, it rises up, it melts, you get the volcano. Other people have argued that there's a hole in the slab or a tear in the slab, which is allowing hot material from the lower mantle to come through. Now, we did a study looking at seismic anisotropy. It's basically, you can look at how the mantle has been flowing over the last sort of tens of millions of years. It aligns crystals. You can measure that looking at seismology. And what we showed is there's a very focused upwelling directly beneath the volcano that we think has to be due to a very small part of the slab that's anomalous, which could be a tear in the slab, or it could be some other feature of the slab that's anomalous that's giving rise to water coming off or something like that. So to answer that, we need those stations in DPRK, right? And ideally in the Japan Sea as well would be very nice, but that's a whole different ballgame of funding and complexities. All right, but that would allow us to look at the slab in much more detail and see whether we can see this tear or not. What was the second question? Oh, yeah. I mean, the ideal would be a bit of both, right? You know, to give us that kind of broadband kind of structure, because the small ones are not as sensitive. So you could get the, you know, real kind of broadband structure, low frequencies, which you don't need the density. And you can go to higher frequencies relying on the kind of dense ones. And that's what we are doing now on volcanoes. So it's a colleague at UEA is just about to go to St. Vincent in the Caribbean and put 200 nodes on a single volcano exactly for that reason, to try and do that.
We have a question from our YouTube audience, and it would be okay, I would understand if you're not able to divulge this information, but they ask, you mentioned that there were alleged nuclear tests during your project. So they want to know, did these show up on your seismometers, and do they tell you anything about the geology that other sources of seismic waves don't?
No, it's a perfectly valid question. So there actually weren't any nuclear tests during our project, which did simplify things. So I think there was one before and one after. So the one I mentioned was in 2016, and that introduced the sanctions. But actually, we'd removed our stations in 2015. The reason we'd love to have kept them longer, but we could get a temporary export license from the UK government. And after 2 years, they wrote to us and said, it doesn't feel very temporary anymore. You probably, you know, we'd extended it twice. They said, you should probably bring them back now. So, okay. So we didn't have them there when any of the tests have happened. So we've never had to deal with that situation.
It's kind of sad to say this is the end of our season for 2024, 2025. We thank you very much for being with us today and for giving a brilliant talk and telling us about these important relations to have as scientists with some very interesting, difficult situations that you are being set up with. So we wish you all the best and the luck with moving forward with your research. And thank you for sharing it with us. Thank you so much, Professor Hammond.
No, thanks, Lucinda. And thanks to the Royal Astronomical Society for the invite. Appreciate it.
We can give her a round of applause. Thank you. There we go. Thank you.